So chapter 5 is all about chemical accounting. Now we're going to get into reactions where we have to do something called stoichiometry. Has anybody heard of the term stoichiometry? Yeah? What do you remember about stoichiometry? It can be difficult, yeah. This chapter takes a lot of time to get good at, so I've got a bunch of practice worksheets for you, and we'll do one of them today. But let's start out with the basics. Start out by talking about a chemical equation. So a chemical equation is pretty common in chemistry, right? It's just a representation of the reaction that's taking place using chemical symbols, right? So let's do an example one, and I'll just make this super generic. So let's say I've got this pretend molecule AB. It can do some sort of reaction and then turn into A plus B. Right, so A and B maybe were covalently bonded together originally, and now they're two separate things. We have to be really careful with how we draw these. In particular, we have to follow the conservation of mass, right? So you see how we have one A at the left-hand side, and then we've got one A coming out? That's called a balanced reaction, and we're going to be spending a lot of time talking about that today. So let's make another note about balanced reactions. A balanced reaction means that there are the same number of elements for the starting materials side and the product side. Really, this is just reiterating the conservation of mass. So we can't create atoms out of nowhere, and we can't destroy them, right? So let's take a look at this, and we'll use a reaction that we did yesterday in lab. So yesterday in lab we took magnesium strips, right? So magnesium is just Mg, and what was the thing we reacted the magnesium with? Does anybody remember the other reagent? HCl, so hydrochloric acid. Okay, so we've got HCl. Okay, so those were our two starting materials. Does anybody know what gas was produced? Was that gas you lit the match and it made that loud chirp noise? Wasn't oxygen, hydrogen, right? So hydrogen in its elemental form is H2. And then for bonus points, what was the other thing that we got out? What do you guys think? Yeah, if we look at our reaction, right, we've got magnesium and chlorine. Those aren't on the product side yet. So now what we need to do is determine what salt can be made using magnesium and chlorine. Is it just going to be MgCl? What do you guys think? You guys are kind of quiet today. So magnesium normally has what charge? +2. It's in that group 2A. And chlorine, on the other hand, has what charge normally? -1. Okay, so we can do that flip where we take this 1 down, we take this 2 over, and that means that the salt we got must have been MgCl2. We don't want to say Mg1 because that's kind of redundant, right? So we're getting magnesium chloride out of this. Do we have to use a Roman numeral when naming it? No, it's not a transition metal. Okay, so this was our overall equation, but is it balanced yet? No. If I look at it, I've got one magnesium on the left, one on the right. I've got one hydrogen on the left, but I've got two on the right. So we need to figure out a way of balancing this. And in order to do this, we use something called coefficients. So we have to determine what multiplier goes in front of each of these in order to make it balanced. So, does anybody have an idea for what we should do? Yep.
Put 2 in front of the HCl.
Okay, put 2 in front of the HCl. Okay, so now if we go through and we check, I've got 1 magnesium here, I've got 1 magnesium here, I've got 2 hydrogens, that's good, and over here I've got 2 hydrogens, and over here I've got 2 chlorines, and over here I've got 2 chlorines. It looks like everything's checking out. So we have to be really careful when we're balancing equations to put in that coefficient number so that we have the same number of atoms on that starting material side as the product side. So use coefficients as multipliers to balance your equation. This is a pretty straightforward example. We're going to ramp up the difficulty a little bit, but it does take a lot of practice to get good at this, which is why I gave you guys a worksheet with like 40 equations to balance. The more you do, the easier it becomes. So let's do some practice before we start doing the worksheet. And I'll give you guys some good hints too. All right, so the first thing I do is I balance one thing at a time. It can be really overwhelming if you try to balance everything all at once. So just focus on one particular element and then balance that. The other thing I do is I leave individual elements until last. If an element's by itself, it's a heck of a lot easier to balance than if it's involved in a complicated molecule. And the third one is if you get stuck, double your most complicated molecule. And then start over. I got to be perfectly honest with you, when you're at your earliest stages with this, it's a lot of guessing and checking, and you may have to go back and erase things and start over again, but that's perfectly fine. Let's take an example. So let's say I've got H2, and I'm reacting this with O2, and we're forming H2O. So hydrogen gas plus oxygen gas, if you burn it, actually forms water. So now what we need to do is we need to figure out the coefficients that go in front of each of these. So what do you guys think we should do? Should we double the hydrogen, double the oxygen, double the water? What would make the most sense? Okay, so if we double the hydrogen, now we've got 4 hydrogens on the starting material side, but we've only got 2 on the product side, so I agree we should double the water. Okay, so now we've got 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, and 2 oxygens on the right. So this is entirely balanced. You don't have to include a 1 in front of the O2. It's implied if you don't include it. So our net equation would look a lot like this if we were to draw out all of our Lewis dot structures. We'd have 2 equivalents of hydrogen gas plus 1 equivalent of oxygen gas, which actually contains that double bond, goes to 2 equivalents of water. So if it helps you to draw it out symbolically using Lewis dot structures, you're more than welcome to. Sometimes it's easy to get confused with these. All right, do you guys want to see this reaction? They won't let me do it in the classroom, unfortunately, so I got a YouTube video. Whoop.
All right, so let's dispel a common belief, and that is that oxygen is combustible. Now, oxygen is not combustible. Oxygen just helps other things that are on fire. It just makes the fire spread a lot further. So here's a balloon, for example, that has nothing but pure oxygen inside, and I'm going to light on fire. All right? Here we go. Pure oxygen. Stand by. Here we go. Watch. See? Nothing at all. Now, if there was something that could catch on fire there, then that would be a whole lot better. So that's where we have this. A bouquet of just balloons for like an ordinary birthday. Except these balloons happen to be filled with hydrogen, and a couple of them happen to have a mixture of hydrogen and oxygen. So I want you to kind of see what this looks like when this goes. And Trustee Jeff here, my assistant, is perfectly safe. You can see no concerns at all. These are my thought protectors, so we are ready to go. Okay? All right, here we go. Ready? Here we go. Wow. Just to prove to you, never use hydrogen for your birthday balloons. This is a public service announcement. Please do not use hydrogen with your birthday balloons. Have a good birthday.
And to put that into some context, that was actually a pretty tame one. I used to do it as a demo until I was told not to. You can blow out windows in a room. The main thing, though, when you're doing this sort of reaction, is you have to very carefully measure out your hydrogen and oxygen. So when you're measuring it out, you have to use twice as much hydrogen gas as oxygen gas in your balloon. And if you hit that ratio just right, it makes a loud boom louder than a gunshot. In fact, we used to have people like 3 stories down come running up thinking that there was some horrible accident. So it's a kind of cool reaction, but a good example of bouncing a chemical equation. So let's do a few practice problems, and then we'll jump into our worksheet. So we'll do these practice ones together. Okay, so let's do another one. We'll do sodium plus water will form sodium hydroxide. It's a strong base, and hydrogen gas. This is a part of the reason that sodium is a flammable metal, is when you throw it into water, it produces hydrogen, which can explode. All right, and then we'll do another one. We'll do silicon tetrachloride plus water. Goes to more complicated molecules, where we make hydrochloric acid. And then for our third one, we'll do phosphoric acid, which is H3PO4, dissociating H4P2O7 plus H2O. And then we'll do a challenge one after this. So let's start with the sodium one. All right, so sodium, we've got 1 on the left, 1 on the right. That looks balanced. If we look at the hydrogens, we've got 2 on the left, and then how many on the right? 3. You have to include the hydrogen on the sodium hydroxide as well as the 2 on the hydrogen gas. So what do you guys think we should do here? Probably double one of them, right? Which one do you think we should double?
Actually,
Multiply everything by 12?
well, 12 and 6.
12 and 6? Let's try to just focus on doubling right now before we start getting into crazy numbers. It'll be a lot easier. Okay, so let's just pick one of them to double. So for example, I'm going to just double our sodium hydroxide. I'm not going to do this hydrogen. Why not? It's a single element. Let's leave that one till last. Okay, so now if we go and look at it, we've got 2 sodiums on the right, but only 1 on the left. So we probably want to double the sodium on the starting material side. Okay, so now our sodiums are balanced. Now if we look at our hydrogens, we've got 2 on the left, and we've got 4 on the right. So we probably want to double our water. Okay, so we'll put a 2 in front of our H2O. So now we double check again. 2 sodiums on the left, 2 on the right, 4 hydrogens on the left, 4 hydrogens on the right. And are we balanced with our oxygens? Yep. So it looks good. We don't have to change anything else. So I normally go with doubling at first, and then if need be, go into more complicated multipliers later on. All right. let's do the same thing with the silicon tetrachloride. So we've got one silicon on the left, and we've got one on the right. So we're good to go there. We've got 4 chlorines on the left, but only one on the right. So I'll go ahead and plug in a 4 over here to bounce the chlorines. Okay, and then we can go to our hydrogens. We've got 2 hydrogens on the left, but now we've got 8 on the right. So what do you guys think we should do? Yeah, I would say put a 4 in front of the H2O. Okay, so now we've got 8 hydrogens on the left. We've got 8 hydrogens on the right. Are we done? What do you guys think? Yeah, it looks balanced to me. So always go through and double check at the end to ensure that you've got everything balanced correctly. And then we'll do the last one. In general, I like to start with the heaviest elements first when balancing. So I've got 1 phosphorus on the left, but I've got 2 phosphorus on the right. So maybe I can double this one over here. So now I've got 2 phosphorus on the left, 2 phosphorus on the right. And then let's go to our next heaviest element, oxygen. All right, so we've got 8 oxygen on the left, and we've got 8 oxygen on the right. So that looks good. And then we go to our hydrogens. We've got 6 on the left, and we've got 6 on the right. So we're good to go. You guys want a challenge one?
Yes.
Okay, let's do a harder one. Is that the same YouTube? Oh, that's just the water one, sorry. So if you've taken a biology course, you've probably seen reactions that look a little bit more complicated. But we'll use a relatively simple one for right now. So hydrocarbons can be oxidized, meaning they react with oxygen, to form CO2 plus water. So we've got ethylene, that's a component of natural gas. We're treating it, whoa, sorry, this should be O2, not O5. That's not a real thing. So we've got ethylene, which is a component of natural gas reacting with oxygen to form carbon dioxide and water. So I'll give you guys a minute to work on this, and then when you think you got it, check with your neighbor. This one requires more work. All right, so let's check in and do this as a group. This one I think is pretty complicated. All right. So in general, we want to leave the simple individual elements till the end, right? So I'm not even going to look at the oxygen right now. I'm only going to look at the C2H2. All right, and like I said, I like to start with the heaviest atoms. In this case, carbon's heavier than hydrogen. So I've got 2 carbons on the left and 1 on the right. All right, easy enough. I'll just double this CO2 over here, right? Okay, and now I look at the hydrogens. I've got 2 hydrogens on the left, 2 on the right. That looks good. And then I look at the oxygens. Last but not least, I've got 2 oxygens on the left, but I've got 5 on the right. What might I do? What do you guys think?
It wasn't an odd number. You just add the double oxygens on the left.
So yeah, if it weren't an odd number, it'd be a heck of a lot easier, right? So now what we might want to do is just start playing around with guessing and checking a little bit. So does anybody want to help me for the next step? What do you think?
Well, you have I started with the C2H2, so I multiplied by 2 there.
Yeah, exactly. That was one of the rules we had where we said if you get stuck, try doubling your most complicated molecule. So in this case, we'll do a 2 here. I think that's a great idea. That's our most complicated molecule. Now we need to go back and rebalance our carbons again though, right? Okay, so we've got 4 carbons on the left. That means we've got to have 4 carbons over here. All right, now we've got 4 hydrogens. Over here we only have 2. So we probably need to multiply that by 2. Okay? Oop. So now we've got 4 hydrogens on the left, 4 hydrogens on the right. Now let's check our oxygens again. We've got 2 oxygens here, and then over here we've got 4 times 2, that's 8, plus 2 over here is 10. So what should we do to the oxygen on the left? Put a 5 in front of it. So like I said, that's a really good strategy to just stop when you get stuck, double your most complicated molecule, and then work through it again. It can be a little bit easier that way. So what I want you guys to do is to grab a practice worksheet, and let's try to get through at least the first half of that front page, and you're more than welcome to pair up with a partner and work through them together. All right, the next topic in chapter 5 is about the mole. The mole is kind of a weird thing in chemistry. I like to call it the chemist's dozen. So like a baker likes to count things using dozens, chemists like to count things using moles, right? So it's a tool used for counting. That's really all it is. And 1 mole is 6.022 times 10 to the 23rd. And this could be anything, so I'll just call it things. So it is an extraordinarily large number. It's a little hard to wrap your head around, so I've got some analogies for you guys. The first one is a mole of baseballs would roughly equal the mass of the Earth. So 1 mole is a huge number of baseballs. The other one is 1 mole of drops of water would be about the mass of all the oceans on our planet. So again, it kind of puts into context the scale of how large a mole is. It is a little bit confusing though. What we are going to have to do a lot of is convert between moles and things. So let's do a warm-up problem for unit conversions. Okay, so how many moles of people are on Earth? Does anybody know the rough population? I pulled it up on my computer. I'm not sure if this is right at all. But I think you're right. It's about 7.5 billion. So 7,311. 278. We'll just say 300. So we need to try to figure out how to convert this number of people into moles. So like I said with unit conversions at the beginning of the term, always start with what you know. And so we know the population. And we need to multiply it. And the unit we want should go on the top, which is moles. And people should go on the bottom to cancel out. And now we need to figure out what number to plug in where. So what do you guys think? Yeah, so the 6.022 times 10 to the 23rd, should that go on the top or the bottom? Well, if we go back up, right? We said 1 mole equals the 6.022, so the 1 should go with the mole. So we'll say 1 mole is the same as 6.022 times 10 to the 23rd. We can plug this into our calculator, but before we do that, how many sig figs should our answer have? 4, right? If we look at this one, this is an approximate value. This has 4 sig figs, which means our final answer should have 4 sig figs. Okay, so let's plug this into a calculator. Does anybody want to help me out? 1.214 times 10 to the negative 14th. Yep. And this would be moles of people. Normally, chemists only use moles for counting molecules or atoms, not people, but this is an example of how you can apply it for anything. It's a pretty easy unit conversion. I will say I want you guys to memorize Avogadro's number, so that 6.022 times 10 to the 23rd. That's the only number I want you guys to remember for this section. All right, so let's talk about a relationship between moles and mass. And this is called molar mass. Molar mass is the mass in grams of 1 mole of something. The nice thing with this is the mass, or the molar mass, I should say, is given to you on the periodic table. So if you look at fluorine, for example, number 9, right below it, it says 19.00. That's the molar mass, so the mass in grams for 1 mole. So it is the same as the AMU mass on the periodic table. So let's do an example. What is the molar mass of helium? What is it? Yeah, so it'd be 4.003 grams of helium per 1 mole of helium. So we can actually use this to convert between the number of moles of something to the mass that it has. Let's do a slightly different one. Let's do the molar mass of Fe. What does Fe stand for? Iron. So if we look at the periodic table, what number is it? It's 26, so it would be 55.84. For every 1 mole of Fe. The important thing to remember is this is just a ratio, right? You can have it right side up or upside down. It doesn't really matter. We could say 1 mole of Fe is equal to 55.84 grams and flip that upside down. It doesn't really matter how you write it. We also need to determine the molar mass of compounds rather than individual elements, but this requires a little bit more work. Not too much work, though. The molar mass of a compound is the sum of all of the elements. So let's take an example. This is calcium chloride, so CaCl2. We need to determine its molar mass. So we want to break this apart. Calcium on the periodic table, if we go over and look at it, is atomic number 20. So that's 40.08, and we only have 1 calcium. So I'll say 1 times 40.08. It's not too bad. And then chlorine over here, we've got 2 of them, so we're going to multiply it by 2 in the beginning. And then the molar mass for chlorine is going to be 35.45. And when you plug all of these in together, you'll have 110.98 grams per 1 mole. So it's not too bad. The big thing you have to remember is to multiply the number of atoms in the molecule. So for chlorine, we had to include that too because we've got 2 chlorines in that molecule. Does that make sense? Let's try a harder one. Let's try glucose. Glucose is the energy that makes our bodies run, or it's the stored energy, I should say. So aerobic respiration uses glucose. Let's figure out the molar mass for one glucose molecule. How much?
164.
Ooh, I'd check your work.
Well, those are decimals, right?
So I'm hearing 164, 180. How about this side of the room? Anybody get it over here? Nobody has their calculator out. You can't just do this in your head. Or if you're really lazy, you can just be, hey Siri, what's the molar mass of glucose? Okay, so you got 180. So let's check our work. We've got 6 carbons. So carbon is 12.01. We've got 6 of them. We've got 12 hydrogens. Hydrogen's atomic mass or molar mass is 1.008. And then oxygen, we've got 6 of them. And its molar mass is 16.00. And at least according to my work, I'm getting 180.16 grams per mole. Does that make sense? All right, so I think that's where we're going to end today. We'll end a little early. And then Monday when we come back, we're going to talk about mole relationships and stoichiometry. But I would really recommend getting through the bouncing equation worksheet before we start getting into stoichiometry.